Hello. Today we will be looking at the second derivative of a function and what it tells us about the graph of the function. Um, so the goal is to determine how the graph of a function curves and to sketch accurate graphs of functions by hand. So mainly we will be looking at what we can say about the graph of a function by looking at its second derivative. In particular, we will be looking at the following question. What does the sign of the second derivative tells us about the graph of the function? Let me start with an example and kind of explain what we are kind of looking for. So let's look at these two functions. One of them is the parabola given by negative x squared. So this is the function f is this parabola, and we are taking x from 0 to infinity. And the function g of x is another parabola, which is the blue one. And again, we are restricting x to be between 0 and infinity. So notice that in both of these graphs, the functions are both functions are decreasing on the interval from 0 to infinity. So both f and g decrease on this interval from 0 to infinity, and both passes through 2 points 0, 0 and 1 comma negative 1. Now the graph of f, which is equal to negative x squared, the graph of this guy is kind of cups downward. So here, notice that at any point on the graph of f, the tangent line lies above the curve. So again, at any point on this curve, the tangent line lies above the curve. So this is what we mean by the curve cups downward here. And we say that this function f is concave down on the interval from 0 to infinity. Now look at the function g of x, which recall is given by a negative root of x. And in this case, notice that at any point on the curve, the tangent line lies below the curve. At any point on the curve, the tangent line lies below the curve. So that's what we mean by this phrase here. So we were saying that g of x cups upward. So we say that g of x is concave up on the interval from 0 to infinity. So basically, what we will see is that the sign of the second derivative will tell us whether a function is concave up or down on a given interval. So the derivative of the derivative, so that's called the second derivative. So the second derivative of a function is the derivative of the derivative function, and it's going to determine such concavity information without needing to graph the function first. So for y is equal to f of x, the second derivative of f is denoted by f double prime of x, and it is defined to be the derivative of the first derivative of f. So f prime of x is the first derivative function of f, and then we are taking the derivative of that one more time with respect to x, and that's the second derivative of f at x. And the other notations that we can use for the second derivative are y double prime or y double prime of x, and also this notation d2y over dx2. So this is the second derivative of y with respect to x twice. Let's do an example and find the second derivative. So y is x squared plus 9 to the 5. And to find the second derivative, we need to find the first derivative. This is if you look at this function, this is a composition where the outside is x to the power 5 is the outside function, and the inside function is x squared plus 9. Now, so another way of looking at it is that, okay, if I look at this function, I wish this is just x to the 5, and if it were x to the 5, then the derivative would be 5x to the 4. So it'll be 5x to the 4, but this inside is not just x, so we need to multiply by the derivative of the inside, which would be 2x. So that's how we use the chain rule. So derivative of the outside, which is 5x to the 4, evaluated at the inside, so you replace x by x squared plus 9 in x to the 4, and then you multiply by the derivative of the inside. Okay, so we get 10x x squared plus 9 to the 4. Now we need to find the second derivative. Now, before we apply the second derivative, we need to realize that this function that we have, the first derivative function, has two factors, each a function of x. So I have 10x. I'm going to think of that as the first factor, and then x squared plus 9 to the 4, that's the second factor. And we apply, we're going to have to apply the product rule. So the second derivative would be the derivative of the first derivative, which is this. And by the product rule, we get the derivative of the first would be 10 multiplied by the second factor plus the first factor 10x multiplied by the derivative of the second factor. Now, the derivative of the second factor, again by the chain rule, would be 4x squared plus 9 to the 3 multiplied by 2x. Okay, so at this point we just have to simplify this, and I'm not going to show you the steps for simplifying. The way you need to simplify is that you can factor out the 10, and you can also factor out x squared plus 9 to the cubed, and then once we factor that out, then we do the algebra, and at the end you get to 90 x squared plus 9 cubed times x squared plus 9. And you should make sure that you can simplify this expression up to this point. Okay, so I hope you understand what is the second derivative now. Now, here is what the sign of the second derivative tells us about the concavity. So if the second derivative of f evaluated at x is positive for any x in the interval from a to b, in the open interval from a to b, then f will be concave up on this interval from a to b. Now, if the second derivative is negative on the interval from a to b, on the open interval from a to b, then f would be concave down on this interval from a to b. Okay, so that's what the sign of the second derivative tells us about the graph of the function. So if I look at the function f of x, which is negative x squared, which was in our first example, Notice that if I take the derivative, so the domain of this function would be, let's say, is all real numbers from negative infinity to infinity. And if I take at the first derivative, then I get 2x. And if I take the second derivative, then I get negative 2. So notice that the second derivative is equal to negative 2 for any x between, for any input x from negative infinity to infinity. So the second derivative is always negative, which tells me that the function is concave down on the entire domain. So since f double prime is negative, f double prime of x is negative for all x, f is concave down on the interval from negative infinity to infinity, and the graph of this guy, this function looks like this. We know this is a parabola that opens downward. Again, notice that at any point on the curve, the tangent line lies above the curve. So the curve always lies below. The curve always lies below the tangent line at any point. So that's why it's concave down. G of x is negative root x. In this case, the domain is from 0 to infinity. And the first derivative is negative half x to the negative half. And the second derivative is going to be 1 over 4 times x to the negative 3/2. Okay, so this is the second derivative. And the question is whether this on this domain here, is this derivative, is the second derivative positive or negative? Well, we can rewrite this as 1 over 4 x to the power 3/2. Now, if x is positive from 0 to, if x is in between 0 and infinity, that is, if x is positive, then clearly g prime of x is positive, and so as a result we see that g is concave up on the interval from 0 to infinity. And if we look at the graph of g, then we see this, and again it's concave up because the curve always lies above any of its tangent lines. The graph always lies above the tangent line at any point on the curve. So it's concave up on this interval. Okay, so let's say we want to use the second derivative to establish the concavity of each of the functions. So let's say number one, part A function is f of x given by e to the negative 2x. Well, the domain of this function is all real numbers, so it's negative infinity to infinity. The first derivative of f is going to be negative 2 e to the negative 2x, and the second derivative would be 4 e to the negative 2x. Well, what do we know about the exponential function e to the negative 2x? Well, we know that it's always positive no matter what x is. So we see that the second derivative here is in fact positive for all real x, and as a result the function is concave up on the interval from negative infinity to infinity. And you can in fact look at the graph of this function, which looks like this. And again, notice that it is concave up. What that means is that the f is concave up. It means that the graph of f always lies above any of the tangent line, lies above the, okay, let me say that again. So f is concave up because the graph of f the graph of f lies above the tangent line at any of its points. Okay, so So in other words, at any point on the curve here, the tangent line lies below the curve. Okay, so here's my second example. G of x is cube root of x plus 1. And the domain would be here all real numbers, because this is an odd root, and so the domain is all real numbers. So the domain is from negative infinity to infinity. What's the derivative of g? The derivative of g is going to be 1/3 x to the negative 2/3. And we can rewrite that, and the second derivative would be, so you take the derivative, you'll get negative 2/3, which would give us negative 2/9, and then you have to subtract 1 from this, which would give us negative 5/3. So that's the second derivative here, which we can rewrite in this way. So look at this second derivative now, and let's ask where is this this derivative positive and where is this negative? Notice that the derivative is undefined when x is 0. So when x is 0, this second derivative is undefined. So I'm going to divide the domain at this point 0 where the derivative is undefined. And now I'm going to say, okay, what is the sign of the derivative when x is negative? Well, notice that when x is negative, this power right here, the cube root of a negative number is negative, and then the fifth power of any negative number is also negative. So when x is negative, the denominator here is negative, but we also have a negative in front, so we're going to get something positive. So when x is negative, the second derivative is in fact positive. On the other hand, when x is positive, then the denominator is positive here, and then we get negative. So in particular, g double prime of negative 1 is positive, g double prime of 1 is negative. So we see that g double prime is positive at any x on the left of 0, and it is negative at any x on the right of 0. So then we see that g is concave up on the interval, or on the left side of 0, and it is concave up on the right side of 0. Sorry, it is concave up on the left side of 0, it is concave down on the right side of 0. So we see that g is concave up from negative infinity to 0, it is concave down from 0 to infinity. Here is the graph of the function that we have looked at. The y is cube root of x plus 1, and you can see that. Remember, at the point 0, when x is 0, the derivative was undefined. So if I go back, notice that the first derivative, because of the negative exponent here, the first derivative is undefined at 0, and the second derivative is also undefined at 0, and that is reflected here. Notice that the tangent line at this point is a vertical line. That is, the y-axis is in fact a tangent line, the tangent line for this curve, and the slope of a vertical line is undefined. So that's why the first derivative is undefined here. But you notice that on the left of 0, the function is concave up, and on the right of 0, the function is concave down. I also want to mention, which we're going to see in a bit, that at this point, at the point 0, 1, the concavity changes from concave up to concave down, and such a point is called an inflection point. That is, it's a point where the concavity changes. So the point 0, 1, which is 0, g of 0, is the point where the concavity changes, and this is called an inflection point of g. An inflection point is a point on the graph of a function where the concavity changes from either up to down or from down to up. If f of c is an inflection point of f, then x is equal to c is a partition number for f double prime. So recall the meaning of this. It means that the c is a critical point. Well, it means that the second derivative either vanishes or 0 at c, or the second derivative is undefined at c. And you can think of those inflection points as the critical points of the first derivative function. Okay, so here is example 4. Let me see how many slides we have done. Okay. Okay, so let's say I want to find the inflection points of the following function. So this is a cubic polynomial. To find the inflection points, we have to first find the first derivative. The domain is obviously all real numbers because it's a polynomial. The first derivative would be 3x squared minus 18x plus 24. And the second derivative would be 6x minus 18. So let's now figure out where the second derivative is undefined and where the second derivative is 0. Obviously, the second derivative is defined for any x. And notice that the second derivative is 0 when x is exactly 3. So that is the only partition number for this f double prime. And the domain of f, we divide that into two pieces right at x equals to 3. Now let's figure out what is the sign of f double prime on the left and on the right of 3. Now if you look at the formula for f double prime, which is 6 times x minus 3, clearly when x is bigger than 3, this quantity is positive, and when x is less than 3, x minus 3 is negative. So when x is bigger than 3, f double prime would be positive. When x is less than 3, f double prime would be negative. So we see this, and as a result, we see that since f double prime is negative on the left of 3, and f double prime is positive on the right of 3, we see that f is concave down on the left of 3, and it is concave up on the right of 3. So since f changes concavity at x equals to 3, the point 3f of 3, which is equal to 3 comma 8, is an inflection point of f. Now how did I get 8? Well, we go back to the formula for the function. So what is f of 3? F of 3 would be 3 cubed, which is 27, minus 9 times 3 squared, so that's going to be 9 times 9, 81, so 27 minus 81, and plus 24 times 3, which would be 72, and then minus 10. So if we simplify that, that's how we get 8. So 3f of 3, which is equal to 3/8, that's the inflection point of this function. And here is the graph of this function. So notice that the function is concave down up to 3. So right here at 3, this is the point 3/8, and up to 3/8 the function is concave down, and after 3/8 the function is concave up. And so again, if you look at the tangent line at any point on the left of 3, it lies above the graph. And if you look at any tangent line, if you look at the tangent line at any point to the right of 3, it always lies below the curve. Okay, so I am going to stop the video here, and in the next video we will be finishing our discussion on this on concavity.